Our universe is a vast and mysterious place. It's filled with billions of galaxies, each containing billions of stars. But how did it all begin? The prevailing scientific theory is the Big Bang. Imagine a tiny point, smaller than an atom, containing all the energy of the universe. This point, incredibly hot and dense, suddenly expanded. This wasn't an explosion in space, but rather an expansion of space itself. From this tiny point, the universe began to grow. It has been expanding and cooling ever since. The Big Bang wasn't just a single event. It marked the beginning of a process that continues to this day. As the universe expanded, it underwent dramatic changes. These changes unfolded in the first fractions of a second, shaping the cosmos we know today. The Big Bang model is supported by multiple lines of evidence. One compelling piece is the redshift of distant galaxies. This redshift indicates that galaxies are moving away from us. It suggests that the universe is indeed expanding. Another crucial piece of evidence is the cosmic microwave background radiation. Discovered in 1965, this faint afterglow provides a glimpse of the universe's early stages. The Big Bang model, though widely accepted, isn't a complete story. It leaves some big questions unanswered. What existed before the Big Bang? What caused it to happen? These mysteries continue to intrigue scientists today. Exploring the Big Bang is a journey to the very edge of our understanding. It's a journey that unveils the awe-inspiring story of our universe's birth. The first epoch after the Big Bang is a period shrouded in mystery. We call it the Planck Era. It lasted for an incomprehensibly short time, from 0 to 10 to the power of minus 43 seconds. To put that in perspective, that's a decimal point followed by 42 zeros and then a 1. During this period, the universe was incredibly small. It was also unimaginably hot and dense. The conditions in the Planck era were so extreme that our current laws of physics break down. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified. They existed as a single, all-encompassing force. However, we lack a theory of quantum gravity. This makes it impossible to describe this era accurately. Imagine a time when space and time themselves were not yet distinct. The Planck era pushes our understanding of physics to its limits. It's a realm where quantum mechanics and general relativity, the two pillars of modern physics, collide. We need a new theoretical framework to understand the universe's behavior during this epoch. Despite the challenges, the Planck era holds crucial clues about the universe's origins. Understanding this period is essential to unlocking the secrets of the Big Bang itself. It's a realm where the fundamental nature of space, time, and the universe's initial conditions might be revealed. Research into quantum gravity and unified field theories may one day illuminate this mysterious epoch. Immediately after the Planck era, the universe underwent a period of exponential expansion. We call this cosmic inflation. In an incredibly short fraction of a second, the universe expanded by an enormous factor. Imagine a grain of sand suddenly swelling to a size larger than our observable universe. This rapid expansion smoothed out the early universe. It stretched any initial quantum fluctuations to cosmic scales. But what caused this sudden and dramatic expansion? The leading theory proposes a field called the inflaton field. This field, thought to have existed everywhere in the early universe, drove the rapid expansion. As the inflaton field decayed, it released its energy into the universe. This energy reheated the universe, setting the stage for the formation of particles and eventually stars and galaxies. The theory of cosmic inflation elegantly solves several cosmological puzzles. For instance, it explains the uniformity of the universe's temperature. Despite its vastness, the universe has a remarkably even temperature in all directions. This uniformity is difficult to explain without inflation. Inflation also provides a mechanism for the origin of the large-scale structure of the universe. The tiny quantum fluctuations present during inflation were stretched to enormous sizes. These fluctuations became the seeds for the formation of galaxies and galaxy clusters. These denser regions grew over billions of years under the influence of gravity. They eventually formed the cosmic web of galaxies we observe today. Cosmic inflation, while still a theory, is a powerful concept. It revolutionizes our understanding of the early universe. Section 4. A cooling cosmos, forces take separate paths. As the universe continued to expand after inflation, it also began to cool. This cooling process had a profound effect on the fundamental forces of nature. In the extreme heat of the very early universe, these forces were unified. But as the temperature dropped, they began to separate or freeze out from one another. Think of water transitioning from steam to liquid to ice. Similarly, the fundamental forces went through phase transitions. First, gravity separated from the other forces. Then, the strong nuclear force became distinct. Finally, the electromagnetic and weak nuclear forces separated. These separations were crucial events in the universe's evolution. The separation of the fundamental forces had profound consequences. It shaped the interactions of particles. It governed the formation of the first elements. The strong force, now independent, could bind quarks together. This led to the formation of protons and neutrons, the building blocks of atomic nuclei. The electromagnetic force, responsible for interactions between charged particles, also played a crucial role. It would later govern the formation of atoms and molecules. The separation of the fundamental forces wasn't just a matter of physics, it was a defining moment for the universe's destiny. It set the stage for the emergence of the structures and complexities we observe today. Section 5. The Dawn of Matter, from Energy to Particles. In the first fractions of a second after the Big Bang, the universe was a hot, dense soup of energy. As the universe continued to cool, this energy began to condense into matter. This wasn't the matter we're familiar with, not yet. Instead, it was a sea of fundamental particles. These particles included quarks, the building blocks of protons and neutrons, and leptons, which include electrons and neutrinos. This era, known as the quark epoch, was dominated by the interactions of these fundamental particles. The universe was still too hot for quarks to combine into protons and neutrons. They existed as free particles, constantly colliding and interacting in the dense, energetic soup. But as the universe cooled further, a crucial transition occurred. Quarks began to combine, forming the first protons and neutrons. This marked the end of the quark epoch and the beginning of the hadron epoch. The universe, though still incredibly hot, was now populated by more familiar particles. This era saw the formation of hadrons, particles made up of quarks bound together by the strong force. Protons, with 2 up quarks and 1 down quark, and neutrons, with 2 down quarks and 1 up quark, became the dominant forms of matter. These particles would eventually come together to form the nuclei of atoms, laying the foundation for the universe as we know it.